Welcome to Night Scientist. If you're watching this, you're probably not looking for noise. You're looking for silence, for calm, for understanding. Maybe you're lying in bed with your thoughts. Maybe you're staring into the dark, letting your mind drift towards something bigger than yourself. Either way, you're in the right place. Our videos are here to keep you company, to ask the questions that never seem to have answers, and to explore the ideas that feel too big to hold. So before we begin tonight's journey, leave a comment below and tell us, where in the world are you watching from? And if you haven't already, subscribe, not just to stay connected, but to remind yourself that you're not the only one wondering. Tonight's question is one of those impossible ones, a question that should be nonsense, a question that bends the mind into knots, and yet, the moment you hear it, something inside you wants to chase it down. If there was nothing, why did anything begin? It sounds like a trick, but it's not. It's the deepest, strangest question we can ask, one that sits beneath everything else, beneath time, beneath space, beneath thought, a question with no clear answer, and maybe no answer at all. So let's begin where everything did, with nothing. But what is nothing? People often imagine a black void, an endless darkness, silent and cold. But that's not nothing. Darkness is still something. Blackness still exists. If you can see or describe it, it's already a form of something. True, nothing is different. It's not the absence of matter. It's not the absence of light. It's the absence of everything. No matter, no space, no time, no energy, no laws, no vacuum. Not even the potential for those things. A total absence. Not empty, but the complete negation of all existence. But if there was ever truly nothing, how could anything have ever begun? This is where our minds rebel. Because in our experience, things don't just happen without cause. Every effect has a reason. Every moment follows the last. You can't make something from nothing. You can't pour water from an empty glass. And yet, here we are. The universe exists. You exist. Everything you've ever seen, heard, touched, or thought exists. Somewhere between the absence of all things and the presence of all things, something changed. 13.8 billion years ago. As far as we can tell, the universe began, not in a place, not at a location within something else, but from nothing. The Big Bang wasn't an explosion in space. It was the moment space itself began to exist. It wasn't a fireball expanding into darkness. It was the birth of time, energy, gravity, structure, all at once. But what triggered it? Some theories suggest that even in the absence of matter, quantum fluctuations can occur, that the universe could spontaneously emerge from the quantum vacuum, a field with zero-point energy governed by the uncertainty principle. In this view, nothing isn't truly nothing. It's more like a simmering sea of probabilities, where tiny sparks of reality can bubble into being. But even this explanation begs a deeper question. Where did that quantum vacuum come from? Where did the laws of physics come from? Why does this strange field of probabilistic energy exist at all? In other words, if we peel back every layer, every cause, every equation, do we eventually find a place where there's truly nothing? And if so, what woke it up? Some scientists argue that this question is meaningless, that asking what came before the universe is like asking what's north of the North Pole. Time itself began with the Big Bang, they say, so there was no before. But even this doesn't fully satisfy us, because it still leaves open the mystery of why anything began at all. Others turn to the multiverse, a grand cosmic landscape where countless universes are constantly forming and dissolving, each with its own laws and constants. Maybe our universe is just one bubble among infinite others. Maybe beginnings are common. Maybe something has always been happening, somewhere. But again, what gave rise to the multiverse? Why does it exist? Why is there anything at all? The ancient philosophers weren't so different from us. Parmenides claimed that nothing cannot exist, that the idea of nothing is a contradiction, because even the concept requires thought, and thought requires something. Other thinkers believed the universe was eternal, that it had no beginning, no creation, just endless being. But then modern science told a different story. The universe is expanding, the galaxies are racing away from each other, and if we rewind that expansion, we arrive at a point, a singularity, where everything we know was once compressed into a space smaller than a single atom. That's the Big Bang. That's the beginning. or at least that's as far as we can see. But knowing when the universe began doesn't tell us why, or how, or what, if anything, came before. Maybe we'll never know. Maybe the question is too big. Maybe our minds, evolved to throw spears and build fires, simply can't grasp the architecture of reality. Maybe nothing is a concept that makes sense in language, but not in nature. Or maybe the question is the key to everything. If there was truly nothing, then the fact that anything exists at all is a miracle, a rupture in the void, a betrayal of the silence. Maybe existence is the default. Maybe nothing is unstable. It always collapses into being. Maybe the laws of logic themselves require something to exist, because non-existence is logically incoherent. But those are just words, guesses in the dark. We don't know why anything began. We don't know if there was ever a true nothing. But we do know this. We are here. You are here, listening, breathing, wondering. That alone is enough to make the question feel real, to make it ache. Because if there was nothing and now there is something, then something changed, something happened. And even if we can't name it, even if it lies beyond thought or time, it connects us to the fabric of reality in a way that's deeply personal. The universe didn't have to exist, but it does. You didn't have to exist, but you do. So we ask the question, not to find an answer, but because asking is what it means to be alive. If there was nothing, why did anything begin? Maybe the question itself is the beginning. Maybe the act of wondering is how the universe becomes aware of itself. In the next part of this journey, we'll dive even deeper into this idea, into the strange, shifting definition of nothing, what it really means, what it can hide, what it might reveal. Because to understand how anything began, we must first understand what it began from. And that is where the mystery truly begins. We speak of nothing as if we know what it means, as if it's obvious, simple, just the absence of something, a place where nothing is. But the more closely we look, the more the concept slips through our fingers, because nothing is not just a word. It's a mirror, a trick of the mind, a doorway into the deepest and most unsettling questions about existence itself. When we say nothing, what are we really imagining? Most people conjure an image, a black void, silent and infinite, empty, still, cold. But even that image is a kind of something, a visual, a space, a feeling. There's distance, direction, darkness, and all of that requires awareness. Your mind is filling in the blanks, constructing a scene, using memory and imagination to simulate emptiness. But the moment you imagine anything at all, the illusion is broken, because real nothing would be the absence not only of things, but of the capacity to imagine them. And here's where the paradox begins. We can't think about nothing without turning it into something. It's the way our minds are built. Our thoughts rely on contrast, on categories, on experience. We understand black by comparing it to white, silence by comparing it to sound, stillness by remembering motion. So when we try to think about nothing, we pull from those contrasts. We subtract things, space, time, matter, until we're left with a fragile image. But what we're left with is still something. A scene of absence is still a scene. It exists. It's shaped. It has texture. It has a frame. And that's why true nothing, if such a thing even exists, might be forever beyond our understanding. Because understanding itself requires a mind, and a mind is already part of something. In physics, the confusion gets even stranger. What we once thought of as empty space, a blank vacuum, is now understood to be buzzing with activity. Even in the total absence of particles, even in the coldest, most desolate patch of space, there is still energy, fields, vibrations, potential. The quantum vacuum isn't nothing at all. It's something quite elaborate, a hidden engine running beneath reality. Tiny fluctuations ripple through this fabric constantly. Particles emerge from the void, live for a fraction of a second, then vanish again. These ghostly flickers can even be measured. They affect the behavior of atoms. They warp space around black holes. They generate the faint whisper of radiation in a supposedly silent universe. And so the deeper we go, the more nothing turns out to be full of structure, full of possibility, full of something. This has led some physicists to propose that our universe began not from true nothing, but from a quantum vacuum, a low-energy state with strange properties, If that vacuum was unstable, it could have collapsed, releasing energy. And from that collapse could have come expansion, gravity, time, matter, the Big Bang. It's an elegant idea. It suggests that the universe didn't need a cause in the traditional sense, that something can arise spontaneously under the right conditions, even if those conditions look to us like nothing. But it still leaves us with an unsettling question. Why was there a quantum vacuum at all? Why do the laws of physics allow it? Why does anything exist to fluctuate in the first place? This is where many explanations quietly fall apart. They provide mechanisms, not origins. They show us how A leads to B, but they don't tell us where A came from. They push the mystery one step back, but the mystery doesn't go away. If the vacuum is something and it created the universe, then we must ask what created the vacuum, and what created the laws that allowed it to exist, to collapse, to explode. We are walking a circle, tracing the edge of a question that has no center. And that brings us back to the illusion. The idea of nothing is compelling because it feels like a clean starting point, a blank page, a total reset. It gives us a way to talk about beginnings. But maybe it's just a shadow we've mistaken for substance. Maybe nothing is not the absence of being, but a trick, a word we use to describe the limit of our perception, a placeholder for the unknown, not a real condition of the universe, but a psychological boundary we keep bumping into, the edge of our mental map. So when we ask, what is nothing, we may not be asking about the universe at all. We may be asking about ourselves, about the way we think, the way we imagine, the way we reach for meaning when we find only silence. But maybe there was never a beginning. Maybe that's the real trick. The moment we say nothing, we imply a transition, a before and then an after. First, there was nothing, then something. But time itself is something. Sequence is something. If there truly was nothing, then there was no time in which nothing could exist, and no change that could cause something to emerge. The entire question might be flawed. We might be forcing a timeline onto a reality that doesn't work that way. And yet, what other tools do we have? We are time-bound creatures. We think in causes and effects. We move through moments, and we crave explanations that start at the beginning and lead to the now. That craving might be leading us astray. In our search for a perfect zero, we overlook the possibility that zero doesn't exist, that it's not a destination, but a direction, a limit we approach but never reach. Think of temperature. Absolute zero is the coldest possible state. No motion, no energy. But even that isn't truly nothing. It's still a state. It still exists within a framework. It's still describable, measurable, calculable. The same may be true for what we call nothing. Every time we try to imagine it, we end up filling it with subtle somethings. A mathematical space, a hypothetical canvas, a field of unrealized potential. We keep using words and images and thoughts, and every one of them betrays the very nothing we're trying to find. Some philosophers have suggested that nothing is not a real thing, but a failure of language, a conceptual dead end, that we're confused not because the universe is mysterious, but because we've built a sentence out of words that don't fit together, like trying to describe the smell of the number 9 or the color of hunger. We're asking for a thing that doesn't and maybe can't correspond to anything real, but that doesn't stop us from feeling it. The fear of nothingness is real. The silence of deep space is real. The chill that runs through the soul when we contemplate the end of all things, that's real too. Maybe we've misunderstood what nothing was ever meant to be. Maybe it isn't the origin of the universe, but a tool, a boundary marker, a way of showing where things end. In that sense, nothing might be less about the beginning and more about death. The absence we fear isn't pre-existence, it's non-existence. The idea that we too could become nothing, that everything we know and love and feel could vanish into that same nameless void. And yet even here, physics offers strange hope. The first law of thermodynamics tells us that energy can't be created or destroyed, it only changes form. Information, some scientists say, is never truly lost. Even in black holes, even in the death of stars, the record of what existed might still remain. Scrambled, hidden, but not erased. If that's true, then maybe nothing doesn't win in the end. Maybe the universe is a story that never fully forgets itself. And maybe in that story, we are the part that asks, that wonders, that looks at the world and dares to say, what if there had been nothing? knowing full well that we cannot answer, and yet asking anyway. There's something deeply human in that, to confront the impossible, not with certainty, but with awe, not to solve the riddle, but to sit beside it quietly and listen to what echoes in its silence. So what is nothing? A paradox, a placeholder, a boundary of thought, a trick our minds play when they brush against the limits of understanding, but also, maybe, a kind of mirror, one that reflects back the richness of being by showing us what isn't there. By imagining the absence of all things, we become more aware of the presence of everything. Every breath, every particle, every star, every question. If there was ever truly nothing, we can't know it. If nothing is real, it is unknowable. And if it's unknowable, maybe that's the same as saying it never existed at all. Time is something we take for granted. We live by it, measure our lives with it, race against it, wait through it. But what if time isn't what we think it is? What if time, the ticking, flowing, arrow-straight stream we build our lives around, is not a universal truth, but a feature of the universe that could one day vanish? Before the Big Bang, time, as far as we understand, did not exist. This is not just poetic, it's mathematical. The standard model of cosmology tells us that time and space emerged together at the birth of the universe. When the universe was born 13.8 billion years ago, it wasn't born into time. Time itself was part of the creation. This idea isn't just abstract theory. It comes from Einstein's general theory of relativity, which shows that time and space are part of a single structure. Space-time. That structure can stretch, bend, and even break under the right conditions. In the earliest moments of the universe, time did not behave as it does now. At scales smaller than a trillionth of a second, during what's called the Planck era, our laws of physics stopped working. Space was compacted, energy density was unimaginably high, gravity was not yet separated from the other fundamental forces, and time? It likely had no direction. It didn't flow forward, because the universe hadn't settled into the kind of ordered complexity that gives time its meaning. You experience the passage of time because entropy increases. Entropy is the measure of disorder in a system. A cup of coffee cools down, smoke drifts upward, buildings decay, memories are made. These are processes that have a direction. The universe moves from states of low entropy to high entropy, from order to disorder, and that change is what gives time its forward arrow. But rewind the tape far enough, and entropy shrinks. In the earliest fractions of a second after the Big Bang, entropy was at a minimum. The universe was nearly perfectly smooth. The laws of physics at that moment would have allowed time to move in either direction. It had no preferred flow. That's one reason physicists sometimes say time didn't exist at the beginning, not because nothing was happening, but because change hadn't yet taken on a direction. There was no before or after, only a quantum fog of possibilities, too compressed and too fast to distinguish moments. But this leads us to something even stranger. Time might not last forever. The heat death of the universe is one of the most accepted long-term predictions in cosmology. As galaxies drift apart and stars burn out, the universe will grow colder and more diffuse. Over trillions of years, energy will spread thin. No stars will remain, no light, no processes, no thermodynamic gradients to drive motion. When entropy reaches its maximum, nothing new will happen. Not because it can't, but because everything that could happen has already happened. And when nothing changes, time, in a practical sense, dies. This idea that time had a beginning and could have an end is deeply counterintuitive. We live our lives inside clocks, but the universe doesn't run on our schedules. Time is not absolute. It's a property of change, and when there is no more change, time has no more work to do. There are other scenarios where time breaks down. Inside a black hole, the curvature of space-time becomes so extreme that our equations collapse. At the center, the singularity, time and space are meaningless. They aren't just distorted, they vanish from our models entirely. Similarly, at the moment of the Big Bang, the singularity at time zero presents the same problem. The physics we rely on today simply do not apply, and that tells us something important. Time, as we know it, may not be the bedrock of reality. It may be a layer, emergent, temporary, fragile. Some physicists go even further. They argue that time itself is not fundamental, but emergent, a byproduct of entanglement in quantum information. In this view, time appears when systems become complex enough to encode a sequence of states. In other words, time is a pattern, a structure, not a fabric beneath the universe, but a shape formed inside it, like a whirlpool in water or a wave in the sea. If that's true, then time isn't something that always was or always will be. It's something that happens, like fire or weather, and like any process, it can end. So we find ourselves in a peculiar place. The thing we use to measure everything, seconds, hours, centuries, may not be a constant of nature. It may have been born when the universe cooled just enough for things to separate and decay and fall apart. It may die when nothing remains to fall further. And in between, we live. We measure time in heartbeats, in sunsets, in the stretch of shadows across the wall. But all these are markers, comparisons between change and expectation. Deep down, time is not an object, nor a flow, but a relationship between events. Without movement, there is no reason for time to exist. It isn't ticking away somewhere in the background. It only exists when something happens. When particles interact, when a process unfolds. That means the edge of time is not found in a calendar or clock, but in the very structure of reality. Now imagine going far, far into the future, past the death of the last star, past the fading glow of white dwarfs, even beyond the decay of matter itself. This is a scenario known as the heat death. It's not sudden or violent. It's slow, empty, cold. It's the eventual fate of a universe that expands forever, stretching space so thin that energy can no longer concentrate. At this point, the cosmos doesn't explode or collapse. It simply stops. No new stars can form. No new light shines. No meaningful interactions remain. The universe is still there, in a sense, but nothing happens. And with nothing happening, there's no way to measure time. The clock keeps ticking, perhaps, but what would be the difference between 1 second and the next if no particle moves, no state changes, and no memory is made? This may be the truest kind of end, not a destruction, but a fading out. Entropy, having reached its peak, would leave the universe without contrast. No gradients, no life, no computation. And if time is bound to change, then time itself would lose meaning. The edges of time, then, are not walls or borders. They're limits to motion, to complexity. When there is no change, the measurement of time becomes irrelevant. But there's another kind of boundary to time, not in the future, but in the past. We've already seen how time as we know it may have started at the Big Bang. But what if it's even stranger than that? What if time didn't begin at a single point, but is an emergent property of structure, something that forms only once the universe becomes interesting enough? This is one interpretation of the Wheeler-DeWitt equation, a formulation of quantum gravity where time doesn't appear at all. In these models, the universe exists as a collection of possible states, but time is not a necessary ingredient. Instead, time emerges when complexity allows the definition of a before and after. Think of it like a still image, unchanging, timeless, until movement begins. Only then do frames become a sequence. In this view, time is not a backdrop. It's something the universe invents, locally, conditionally. Some theoretical physicists go further. Julian Barber, for example, has proposed that what we perceive as time is simply a reflection of the difference between two configurations of the universe, what he calls time capsules. According to this idea, time isn't real in the way we think it is. All the moments we experience, past, present, future, may exist simultaneously as a set of frozen states, and our consciousness merely gives the illusion of flow. In that framework, there is no before the universe began. There is no ticking. There are only snapshots connected by memory and experience. If that sounds difficult to believe, you're not alone. Time feels real. It hurts when it passes. But just as we once believed the earth stood still while the sun moved across the sky, our intuitions aren't always reliable guides to the universe. We may be creatures born inside a system where time exists only locally, temporarily, an accident of energy and entropy, a condition that arose when the universe expanded and will vanish when it ceases to change. Still, there's meaning in all of this. Even if time is temporary, its presence is not an illusion. It shapes what we can do, what we can know, and how we evolve. It gives us cause and effect, motion and memory, life, and loss. If time began, and if it will end, then every moment we experience becomes more precious, not less. Every second is borrowed from a universe that doesn't guarantee anything. The death of time isn't just a concept on a blackboard, it's a reminder that what we feel slipping through our fingers each day is not infinite, that we exist briefly in a cosmos where time still moves forward, and that our place, here and now, exists only because the universe still changes. We live at the edge, the narrow slice between the timeless past and the timeless future, a flicker between stillness and silence, and in that flicker there is meaning. If the universe came from nothing, then the first place to look for an answer isn't in empty space, but in the rules that govern the smallest things imaginable. At quantum scales, the world becomes unrecognizable. Objects behave like waves, certainties dissolve into probabilities, and emptiness is never truly empty. Quantum field theory, our most successful model of subatomic behavior, tells us that every type of particle is associated with a field that stretches across all of space. Even when that field is at its lowest possible energy, it doesn't rest, it fluctuates. Particles spontaneously appear and vanish in the vacuum. They are called virtual particles, not because they're imaginary, but because they exist so briefly that they can't be directly observed. And yet their effects are real. They influence atomic behavior. They produce measurable changes in energy levels. They've even been detected indirectly in what's called the Casimir effect, where two metal plates placed very close together in a vacuum experience a force pulling them inward, a force caused by quantum fluctuations in the empty space between them. This quantum vacuum isn't the kind of nothing we might imagine when we hear the word. It's not a blank void, it's a boiling sea of possibilities. Even at its lowest energy state, it's teeming with activity. And in certain conditions, these fluctuations can do more than produce tiny sparks. They can produce real particles. In high-energy environments, like near black holes or in particle accelerators, quantum fields can be pushed into new states, giving rise to matter. This is the basis for one of the most intriguing theories of cosmic origins, that the universe itself emerged as a fluctuation in a quantum field, not a reaction to something else, not a collapse, but a spontaneous event, a statistical anomaly that just happened to produce everything. To understand how, imagine this. The vacuum of space is not flat, not passive, but filled with quantum tension, like a tightly stretched sheet. Occasionally, that sheet ripples. Most ripples cancel out. They rise and fall, leaving no trace. But if a ripple is large enough or strange enough, it might not fade. It might tunnel into a new state, one that contains mass, energy, and expanding space. That ripple, once stabilized, becomes what we call a universe. This is called quantum tunneling, a phenomenon where particles overcome energy barriers they have no right to cross, simply because at the quantum level, rules behave like probabilities. It's as if a ball sitting in a valley spontaneously appears on the other side of a hill without climbing it, because the rules of the micro world allow it. This isn't speculation. It happens in radioactive decay and in semiconductors, and we've built technology around it. Now scale that concept up. Imagine the universe, everything we see, as a tunneling event from a higher energy vacuum to a lower energy one, a kind of cosmic phase shift. If space is a field and fields can shift between states, then maybe the Big Bang wasn't the start of everything, but the result of one such shift, a point where the quantum vacuum transitioned into something with direction, time, energy, and law. But this opens new questions. What governed the rules of that transition? What determined the nature of our universe's constants, gravity's strength, the speed of light, the charge of an electron? Why did those particular values emerge instead of others? These are the fine-tuning puzzles, the cosmic dials that seem, by all appearances, precisely adjusted to allow galaxies, stars, chemistry, and life. Change any one of them slightly, and the universe would expand too fast for stars to form, or collapse before anything could evolve. Some scientists see this as chance, others as necessity. Others still wonder whether we're just one of many, that the quantum field has produced countless universes with different parameters, and we happen to live in the one that works. That's the multiverse hypothesis, born from the same quantum principles that allow fluctuations and tunneling. If quantum foam can produce one universe, why not many? And if all possibilities exist in the sea of randomness, then most of them would lead to dead ends, failed realities, lifeless worlds. Ours is simply the lucky draw. Still, even these elegant explanations rely on something: quantum fields, fluctuations, probabilities, equations. None of them emerge from pure nothingness. They are built into the framework of reality itself. So even as quantum theory shows us that particles can pop into being without cause, it also assumes a backdrop, a law, a field, a landscape that allows for it. The question remains, where did that come from? The universe, as described by quantum physics, is never quiet. Even when stripped to its most basic state, a vacuum with no particles, no radiation, no discernible energy, it still hums with invisible motion. This background activity built into the quantum fields themselves is more than theoretical. It shapes everything: the atoms in your body, the light from distant stars, the very stability of matter. And yet, for all its success, quantum theory cannot tell us where these fields came from. They simply exist. They are written into the foundation of physics like the grammar of reality. There is no equation that predicts their existence, only ones that describe how they behave once they exist. And that is a subtle but important distinction, because if we're asking whether something can come from nothing, we can't simply describe how something behaves. We have to ask whether the framework itself could emerge from non-being. To answer that, some scientists and philosophers look toward the idea of symmetry breaking. In the earliest moments after the Big Bang, possibly even before the universe had taken its current shape, the laws of physics may have been unified. All the forces we know today, gravity, electromagnetism, the strong and weak nuclear forces, may have been identical, folded together into a single force. But as the universe expanded and cooled, this symmetry broke. The forces separated, distinctions formed, and structure followed. This idea explains why particles behave differently under different conditions, and why certain constants appear finely tuned. But again, the process assumes a prior state, a canvas with rules, even if the rules were simpler then. So we circle back. If symmetry can break, then what symmetry existed before? If fields can ripple, what gives rise to the field? Even the idea of quantum nothing starts to look suspiciously like something, just in disguise. There are some who believe we're asking the wrong question. Instead of looking at reality and asking, where did this come from? Perhaps we should ask, why should there be nothing? The assumption that nothingness is the natural state and somethingness is a deviation might be backwards. Some physicists, such as Edward Trine, have proposed that the universe could be a large-scale quantum fluctuation, not from nothing, but from a kind of zero net energy state. In this view, the total energy of the universe, matter, radiation, gravitational potential, may add up to exactly zero. If so, the universe isn't breaking any rules by existing. It's borrowing nothing from nothing. It's a cosmic balance sheet that always adds up. But while elegant, this is still a theory that works inside a framework, one that allows energy to exist, to be positive or negative, to cancel itself out. And here lies the edge of current science. We can trace the origins of matter, energy, structure, and time to moments after the Big Bang. We can describe quantum fields, calculate their behaviors, and test them in high-energy environments. But the question of the origin of the framework, of the laws themselves, remains unsolved. Why do they exist at all? Why is there a fabric for quantum ripples to form in? Why should physics allow for universes to form, to expand, to cool, to evolve? Some modern cosmologists believe this question may never have a scientific answer. It may be fundamentally inaccessible, not because it's mystical, but because it lies outside the bounds of empirical testing. Science depends on observation, prediction, and falsifiability. But if the origin of the laws themselves can never be tested, then it may sit forever in the realm of informed speculation. Yet even that speculation can lead somewhere meaningful. Some propose that the laws of physics are not fundamental at all, but emergent, that they arise from deeper principles or from statistical patterns across enormous systems. Think of temperature. It's not a property of any single atom. It emerges when trillions of atoms move in relation to each other. In the same way, what we call laws may emerge from deeper informational structures, logic, symmetry, or pure mathematics. That leads us into more radical territory. Theoretical physicist Max Tegmark has proposed the mathematical universe hypothesis, the idea that the universe is not just described by math, but is math. that all structures that can exist mathematically do exist somewhere, and we happen to inhabit one of them. In that picture, there's no need for a creator, a spark, or a cause. The universe simply is, because its structure allows it to be. There is no nothing because mathematical possibility is itself a kind of existence. Of course, not everyone agrees. These ideas stretch the meaning of existence, and the line between science and philosophy becomes thin. But what they reveal is that the deeper we explore the quantum roots of reality, the less certain we become about where the boundary between nothing and something actually lies. Maybe there was never a clean separation. Maybe nothing and something were never opposites. Maybe they are phases of the same process, with the universe as the ripple and quantum fields as the still water it emerged from. Whatever the case, the scientific quest continues, not to prove that the universe came from nothing, but to understand the rules that allowed anything to emerge at all. When we talk about the beginning of the universe, we usually start with the Big Bang. It's a term that has captured the imagination for decades, a cosmic explosion, a fireball expanding into space, the moment when everything began. But the truth is far stranger. The Big Bang wasn't an explosion in space. It was the birth of space itself. There was no outside, no silent vacuum waiting to be filled. There was only this, a singular moment where time, space, energy, and the laws of physics themselves unfolded from an origin point that we still don't fully understand. The evidence for this moment is overwhelming. When we look into deep space, we are also looking back in time. And the farther we look, the younger the universe appears. Galaxies are moving away from us in every direction, and the space between them is expanding. This isn't because the galaxies are flying through space, it's because space itself is stretching. This observation led to the idea that, long ago, everything we now see was once compressed into a single, incredibly hot, dense state. From that point, roughly 13.8 billion years ago, the universe began to expand, and as it did, it cooled. In the first moments, energy was so intense that matter couldn't even form. Quarks and gluons swirled in a hot plasma. Then, as temperatures dropped, those particles began to bind into protons and neutrons. A few minutes later, atomic nuclei formed. Hundreds of thousands of years after that, atoms finally became stable, and light could move freely for the first time. That ancient light is still with us today. It's called the cosmic microwave background, and it's one of the strongest pieces of evidence for the Big Bang. But even with all this, we still don't know what, if anything, caused the Big Bang. In fact, the phrase Big Bang can be misleading. It gives the impression that it was a single sharp event, like a balloon popping, when in reality, it was a smooth, rapid unfolding. The term itself was coined somewhat sarcastically by astronomer Fred Hoyle, who didn't believe in it. He preferred a steady-state universe, one that had no beginning or end. But over time, the evidence piled up: redshift, background radiation, the abundance of light elements, all pointing to a beginning. So what do we really know about this beginning? Technically, the Big Bang Theory doesn't describe the origin of the universe. It describes its evolution after the initial moment. The theory works beautifully from a fraction of a second onward. But at time zero, what we call the singularity, our equations break down. General relativity and quantum mechanics both fail to describe what's happening there. Space and time themselves become undefined. Density and temperature approach infinity, and no known physics can make sense of that state. This doesn't mean it didn't happen, it just means we don't yet have the tools to explain it. To get closer to the truth, scientists have explored various ideas that go beyond the classical Big Bang. One of the most important is cosmic inflation. According to this theory, in the tiniest fraction of a second after the universe began, around 10 to the power of negative 36 seconds, the universe underwent an unimaginable expansion. It didn't just double in size, it expanded by a factor of 10 to the 78th power. This inflation smoothed out any irregularities and explains why the universe looks so uniform on large scales today. The theory of inflation also predicts the tiny fluctuations we now observe in the cosmic background radiation, variations that eventually became galaxies, stars, and planets. But what triggered inflation, and what came before it? Here we hit the wall again. Inflation tells us what happened right after the beginning, but not how or why that beginning occurred. Some versions of inflationary theory suggest that inflation itself is eternal, that it keeps happening in different regions of space, spawning multiple pocket universes, each with their own properties. In this view, our universe is just one bubble in a vast cosmic foam. But again, this pushes the origin question back, not away. If inflation created our universe, what created inflation? Another possibility is that the Big Bang wasn't a beginning at all, but a transition, the bounce between a previous contracting phase and our current expanding one. This is the cyclic model, where universes rise and fall in an eternal cycle. It offers a kind of solution to the problem of time and cause. No beginning, no end, just transformation. But even then, we're left wondering how the cycle began and why it exists in the first place. Each of these ideas, inflation, quantum fluctuations, cyclic universes, gives us partial answers. They describe what could have happened and how one state might lead to another, but none of them fully explains why anything exists at all, or why it started when and how it did. What makes the Big Bang so mysterious isn't just its scale or energy, it's that it seems to defy causality. In our world, effects have causes. Things don't happen without reason, but the Big Bang appears to be an event without a before, a change with no prior state. And that's why some physicists describe it not as an explosion or even a moment, but as a boundary, a limit to what our current science can describe. If the Big Bang marked the beginning of everything, of space, of time, of the very rules by which things interact, then the idea of a cause becomes extremely complicated. In everyday life, causes come before effects. A match lights and then it burns, a stone falls and then it hits the ground. But in the Big Bang, there is no before. Time begins with the universe. So how can something have a cause if there is no time in which the cause could have happened? This is where the Big Bang starts to challenge not just physics, but intuition itself. We're built to understand sequences. We live inside timelines. But if time itself had a beginning, then asking what happened before is like asking what's north of the North Pole. It's not just unknown, it's undefined. There is no before the beginning of time. Some physicists suggest that this means the Big Bang didn't need a cause in the traditional sense. Instead, it simply was. A boundary condition, like the edge of a painting. A starting point not because something pushed it into motion, but because there was no alternative. In mathematics, certain solutions exist only if you accept specific boundary conditions. The universe may be like that, a structure that only exists if time begins at zero. In this view, the Big Bang is less like an event and more like the edge of a map, the place where the terrain ends and nothing can be drawn beyond it. It's not that something happened at time zero, but that time zero is the point at which events become possible. Before that, even the concept of happening breaks down. This concept isn't purely philosophical, it's supported by models in quantum cosmology. In particular, the Hartle-Hawking no-boundary proposal, developed by physicists James Hartle and Stephen Hawking, suggests that the universe didn't begin in a singularity at all, but rather in a smooth, rounded state where time behaves like a spatial dimension. In this model, the early universe is finite but unbounded. Like the surface of a sphere, there is no edge, no corner, no singular starting point. Time emerges gradually as the universe expands and cools. The result? The universe has no sharp origin, and therefore no need for a cause in the classical sense. This is difficult to grasp because we are so used to asking why. Why did the Big Bang happen? Why at that moment? What made it occur? But these questions rely on assumptions that may not apply to the universe as a whole. They assume that causality, the link between cause and effect, is fundamental. Yet in quantum mechanics, cause and effect aren't always so clear. Events can be probabilistic. Outcomes can exist in multiple states at once. In some interpretations, particles don't choose their properties until measured, and sometimes particles influence each other in ways that seem to transcend time entirely, a phenomenon known as quantum entanglement. All of this suggests that causality, like time, may be a feature of the universe, not a foundation beneath it. If the early universe was governed by quantum rules, then asking what caused the Big Bang may be like asking what causes a quantum fluctuation. It's not caused, it's allowed. It occurs because the conditions permit it, because the probability isn't zero, and once it occurs, everything else follows. That brings us to another question. Is the Big Bang unique, or do universes appear all the time, each with their own beginning, their own arrow of time, their own constants? The multiverse theory proposes that what we think of as the universe is just one bubble in an infinite foam of possibilities. In this picture, big bangs are not rare, they are common, maybe even inevitable. Each new region of space that undergoes inflation creates a new pocket universe with its own timeline and laws. If this is true, then our universe's beginning doesn't need a cause in the cosmic sense. It could simply be one of countless spontaneous events. A fluctuation, a phase change, a ripple in a much larger system. But here too, we find the question pushed back rather than resolved. What caused the multiverse? What allows for fluctuations in the first place? What rules govern the background where universes are born? No matter which model we choose, quantum fluctuation, no boundary condition, eternal inflation, we end up face to face with a strange conclusion. The universe may not have a cause, at least not in any way that resembles our normal understanding of cause and effect. Instead, it may be the result of laws that exist outside of time. Laws that don't change, don't begin, and don't end, because they are not events. They are truths, frameworks, conditions of possibility. And yet, even if the Big Bang needs no cause, that doesn't make it meaningless. On the contrary, it may be the most meaningful boundary in existence, the moment that made all other moments possible. A beginning not because something came before it, but because nothing did. The Big Bang may have marked the beginning of time, but that hasn't stopped physicists from wondering what, if anything, came before it. At first glance, the question sounds meaningless. If time begins with the Big Bang, then how can there be a before? It's like asking what's earlier than the first second, or what lies north of the North Pole. But that hasn't discouraged science. In fact, it's opened new pathways for thinking, paths that challenge our assumptions about time, space, and the structure of reality itself. For decades, the Big Bang was seen as the ultimate origin, a singular event from which all things flowed. But singularities are problematic. In general relativity, a singularity is a point where density and gravity become infinite, and the laws of physics break down. Infinite values are a sign that our equations have lost their meaning. Most physicists now believe that the singularity at the beginning of the universe isn't a real physical object, but a signal, a boundary in our knowledge. And so, to go further, we need to look beyond standard cosmology. One idea gaining traction is that the Big Bang wasn't the beginning of everything, but the beginning of our phase of the universe. Just as ice melts into water or water boils into steam, the universe could be undergoing transitions, large-scale phase shifts that transform its structure. In this picture, what we call the Big Bang may have been the end of something else, not nothingness, but a different kind of space-time, something more compressed, something curved differently, something collapsing. This is the core of the bounce models, a class of theories that imagine the universe not beginning from scratch, but emerging from a prior contraction. Instead of exploding from nothing, the cosmos may have rebounded, shrinking in on itself until reaching a minimum size, and then expanding again. These models are attractive because they eliminate the singularity. There is no moment of infinite density, no breakdown of physics, just a bounce, like a ball hitting to the ground and flying back up. One version of this idea is called the ekpyrotic model, inspired by string theory. In this framework, our universe exists on a three-dimensional membrane, or brane, floating within a higher dimensional space. Occasionally, branes collide. That collision transfers energy, sparking a new cycle of expansion, a new universe. Each collision could be a new Big Bang. The previous universe doesn't disappear. It just leads to the next. Another variation is the conformal cyclic cosmology proposed by Sir Roger Penrose. In this model, each phase of the universe, from Big Bang to heat death, is called an aeon. At the end of one aeon, when the universe is cold and empty and all matter has decayed, its geometry becomes conformally flat, essentially timeless. This smooth, scale-free state can then be mapped onto the beginning of a new Big Bang, creating a fresh aeon. Time starts again, not from nothing, but from the stretched remains of a previous cosmic era. These theories are not just imaginative speculation. Some of them make testable predictions. For instance, certain bounce models suggest there could be imprints from a previous universe embedded in the cosmic microwave background. The faint glow left over from the early universe, patterns in this radiation, tiny temperature fluctuations, may carry echoes from an earlier phase. So far, the data is not conclusive, but it's an active area of research, and new observations from next generation of space telescopes may bring answers in the coming years. Still, none of these ideas solve the ultimate question. What started the first cycle? What created the brains? Where did the higher dimensions come from? Whether you believe in a single Big Bang or an infinite sequence of bounces, the issue of a true beginning still looms. Even if time stretches infinitely into the past, we're left asking, why is there anything at all to stretch? Some scientists argue that maybe there is no beginning, not because the universe is eternal in a simple way, but because beginnings themselves are human concepts. They arise from our experience of time as a flowing, linear process, but in the language of physics, time can be far more flexible. It can bend, stop, even emerge from deeper, timeless structures. In some quantum gravity models, time is not fundamental at all. It appears only when certain conditions are met. In this view, there is no before or after, only relationships between states. That doesn't make the question meaningless, only more subtle. Maybe we don't need to imagine a first cause or a hard origin. Maybe the universe didn't start. Maybe it just is, an eternal system, constantly reshaping itself, with no beginning and no end. Or perhaps the beginning is real, but it's not the kind we understand yet. Not a moment, not a point, but a transformation from something more abstract than space and time. As we reach deeper into the question of what came before the beginning, the limits of our current understanding become clearer. The further back we try to peer, the more the picture blurs. Not because we lack data, but because the very language of time and cause may stop applying. Yet, this hasn't stopped scientists from developing more sophisticated tools to explore the frontier. One of the most promising frameworks is loop quantum gravity, a theory that attempts to reconcile general relativity with quantum mechanics. Unlike string theory, which imagines particles as tiny vibrating strings in multiple dimensions, loop quantum gravity suggests that space itself is made up of discrete loops, tiny indivisible units of volume. In this model, space is not continuous, but quantized, like pixels on a screen. And most importantly, loop quantum cosmology, the application of this theory to the entire universe, predicts that the Big Bang singularity is replaced with a bounce. This bounce isn't just mathematical speculation. It emerges directly from the equations, which show that when the universe becomes dense enough, close to the Planck scale, quantum geometry takes over. Gravity becomes repulsive, not attractive. Instead of collapsing into a singularity, the universe rebounds. This provides a natural explanation for the origin of the expansion without invoking a cause in the classical sense. The bounce is just what happens when the density reaches a critical threshold. What's fascinating is that loop quantum gravity doesn't require time to pre-exist. In this view, time itself may be emergent, not something that flows independently, but something that arises from change in the configuration of quantum states. In a pre-bounce state, time as we know it might not exist. There would be no sequence, no ticking clock, only a timeless quantum foam, governed by laws that don't rely on duration. When the bounce occurs and the universe expands, the conditions for time emerge. In this sense, asking what came before the Big Bang may be equivalent to asking what happened before time itself existed, a question that can only be answered by redefining what before even means. Other models explore even more unconventional terrain. One is the emergent universe scenario, in which the universe exists in a stable, eternal state before inflation. This pre-inflationary universe isn't expanding or evolving, it's static, a cosmic seed waiting for the right fluctuation to ignite growth. When that fluctuation occurs, inflation begins, and the universe we see today unfolds. In this model, there is a kind of before, but it's unchanging, like a dormant field of potential waiting to be disturbed. Again, the idea of time is twisted, not absent, but frozen. These ideas highlight a key trend in modern cosmology, the notion that beginning may not mean what we think it does. In classical thinking, beginnings are sudden, sharp, and caused. A match lights, a universe expands, but in quantum cosmology, beginnings can be smooth, slow, or even imaginary. In fact, some models, like the Hartle-Hawking no-boundary proposal mentioned earlier, describe the origin of time using imaginary numbers. This isn't science fiction, it's mathematical physics. In their model, the universe begins not in a point, but in a rounded geometry, where a time is treated as a complex number, transitioning into real time only after a certain threshold. There's no hard edge, no singularity, just a shift from timelessness to time. This doesn't mean we'll never understand what came before. It means we need to upgrade our thinking. We've already done it before. We once believed the Earth was the center of the cosmos. We once believed time was absolute, ticking the same for all observers. Now we know time stretches and warps, that space curves, that particles can be entangled across light years. It's entirely possible that, before the beginning, will eventually be described not with words like before or nothing, but with entirely new terms, mathematical, logical, and unfamiliar. Until then, our best model suggests that if there was a before, it was radically different, a state without particles, without expansion, possibly without time, a framework governed not by clocks but by probabilities and quantum relationships. What followed wasn't a bang, but a transition, a bounce, a bloom, a rearrangement of conditions that suddenly allowed reality, as we know it, to unfold. And perhaps that's enough. We may never see what came before the beginning, but the fact that we can model it, imagine it, simulate it, that we can follow the clues embedded in the sky, in background radiation, in the mathematics of existence, speaks to something extraordinary. The universe may be vast, ancient, and mysterious, but it also speaks in patterns, and we are slowly learning how to listen. What if the universe, the entire cosmos that holds every star, galaxy, planet, and atom, is just one among countless others? This idea, once the realm of science fiction and philosophical speculation, has become a serious proposal in modern physics, the multiverse. At first glance, it sounds like a drastic claim. One universe is already vast beyond comprehension. It stretches over 90 billion light years across, and possibly more, depending on what lies beyond what we can observe. But the multiverse suggests that our universe is merely a patch, a bubble in a far larger, possibly infinite structure. And this idea didn't come from fantasy or imagination. It came from the attempt to understand how our universe began and why it has the properties it does. One of the earliest clues comes from the theory of cosmic inflation, the idea that in the first fraction of a second after the Big Bang, the universe expanded at an exponential rate. This inflation smoothed out any irregularities and made the universe look remarkably uniform across great distances. The theory solves many cosmological puzzles, and its predictions have matched what we see in the cosmic microwave background. But inflation, once started, doesn't stop everywhere at once. In many models, inflation continues forever in some regions, while stopping in others. The places where it stops become universes like ours. The places where it continues go on generating new universes. This is called eternal inflation, and it leads naturally to a multiverse. Each of these pocket universes could have different physical conditions, different laws of physics, different values for constants like the strength of gravity, the mass of particles, or the charge of the electron. In some, stars might never form. In others, atoms might not be stable. Most of these universes would be sterile, but a few, like ours, would have just the right ingredients to support complexity, chemistry, and eventually, life. This idea helps answer a question that has long puzzled scientists. Why do the laws of our universe seem so finely tuned for life? The physical constants of our universe fall within incredibly narrow ranges. If they were even slightly different, the universe would look completely different. Stars wouldn't form, carbon wouldn't exist, planets might never coalesce. Some physicists find it suspicious. It's as if the universe is set up for life to emerge. But in a multiverse, this isn't surprising. If there are infinite or near infinite universes, each with random parameters, then it's not surprising that at least one, ours, happens to have the right settings. We exist here because this is the kind of universe where observers can exist. This is called the anthropic principle, the idea that our observations of the universe are shaped by the fact that we're here to observe it. In other words, we shouldn't be surprised to find ourselves in a universe that supports life, because we couldn't exist in one that didn't. The multiverse isn't a single theory, though. It's a family of ideas emerging from different parts of physics. Eternal inflation is one source. String theory provides another. In string theory, all particles are tiny vibrating strings. The way these strings vibrate, and the geometry of the extra dimensions they move through determines the properties of the universe, but string theory allows for an enormous number of possible configurations. Some estimates suggest there could be as many as 10 to the power of 50 different vacua, each representing a different possible universe with different physics. This landscape of possibilities has led many physicists to propose that all of these universes actually exist, not as hypothetical variations, but as real physical realities, each with its own space-time, laws, and history. We just happen to live in one. There's also the many worlds interpretation of quantum mechanics, a radical but increasingly popular idea. It suggests that every time a quantum event occurs, say a particle going left or right, the universe splits. Both outcomes happen, but in different branches of reality. In this view, the multiverse is constantly branching into new universes. Every decision, every particle interaction, every coin toss spawns a new world. The implications are staggering, an infinite number of versions of you, each living out different possibilities. While these ideas differ in detail, they all share a common thread. The universe we see may not be all that exists. There may be countless others. And if that's true, then the Big Bang wasn't the birth of everything, only the birth of our bubble, our patch of the multiverse. The multiverse offers an enticing framework, one that could explain not only the origin of our universe, but why its laws appear so perfectly balanced for complexity in life. But as bold and far-reaching as the idea is, it also comes with serious challenges. And the biggest one is this: if we can never observe these other universes, how do we know they're real? Science, at its core, is about testable predictions. If a theory can't be verified or falsified, then many argue it stops being science and becomes speculation. That's the main criticism aimed at the multiverse. While models like eternal inflation and string theory lead naturally to the idea of multiple universes, those other universes are, by definition, causally disconnected from ours. They're beyond our cosmic horizon, too far away, too separate to ever send us a signal. No telescope, no detector, no experiment could confirm their existence, at least not directly. Some physicists argue that this makes the multiverse more of a philosophical framework than a physical theory. It may help organize ideas or explain why our universe has the properties it does, but without observational evidence, how can we treat it as more than an elegant narrative? Supporters of the multiverse idea counter with a different perspective. They point out that the theory isn't pulled from nowhere. It's a prediction or consequence of other well-supported theories. Inflation, for example, was developed to solve real problems in early universe cosmology. It explains why the universe appears flat, why it's so uniform across vast distances, and why the cosmic microwave background has the patterns it does. These predictions have been tested and confirmed, but if inflation is correct, then eternal inflation, and by extension, a multiverse, may follow naturally. In that sense, even if we can't observe other universes directly, we may still have indirect evidence. By observing the universe we do inhabit, some researchers have even proposed ways we might detect signs of interaction. For instance, if another universe collided with ours in the distant past during its inflationary phase, it might have left a mark in the cosmic microwave background, a cold spot, a distortion, or an unexpected pattern. So far, no definitive signature has been found, but the search continues. Others look at the idea statistically. If the space of possible universes is vast, as string theory suggests, and we find ourselves in one that supports life, then the anthropic principle becomes more than philosophical hand-waving. It becomes a kind of reasoning. In an ensemble of universes, observers will always find themselves in the ones where observation is possible. This may not feel satisfying. It doesn't give us a mechanism or a cause, but it could explain why the universe appears so improbably suited for life, not because it was designed that way, but because only such universes can contain beings like us. Still, for many physicists, this raises a difficult question. When does explanation become evasion? Are we invoking a multiverse because it's supported by deep theory, or because it's convenient? If we accept every unexplained feature of our universe as just one version out of many, do we risk giving up on the search for deeper principles? There is also the issue of predictability. If all possible universes exist, then how do we test any prediction? If there's a universe where gravity is stronger, one where light travels faster, and one where no chemistry forms at all, then any observed condition in our universe could be seen as just one point in a sea of outcomes. This makes the theory difficult to constrain or refine. Despite these concerns, the multiverse remains a powerful idea, not just because it offers possible answers, but because it reflects a deeper trend in science, the expansion of perspective. Every major shift in our understanding has moved us outward. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The galaxy was not the center of the universe. Perhaps our universe is not the whole of reality. And if that's true, then the story of our origin becomes one chapter in a much larger book. The Big Bang was not the singular beginning of existence, but a local unfolding. The laws of physics are not absolute, but regional. And we, observers, thinkers, wanderers, are not anomalies, but natural products of a universe that happens to support awareness. Perhaps the most sobering implication of the multiverse is that we may never have access to ultimate answers. If we live in one of infinite possible universes, then some features of our world may have no deeper explanation than this. They are the way they are, because they could be, and because we are here to notice them. But that doesn't mean the quest is meaningless. On the contrary, understanding that we may inhabit one possibility among many invites us to explore more deeply the nature of those possibilities. It challenges us to refine our theories, improve our models, and perhaps one day find evidence of realities beyond our own. Because even if we are one bubble in a sea of cosmic foam, the bubble still matters. It contains light, it contains structure, and it contains us. At first glance, the laws of physics seem remarkably specific. The speed of light is exactly 299,792,458 meters per second. The gravitational constant has a precise value. Electrons carry a fixed negative charge. None of these numbers had to be what they are. They could have been different, and if they were, the universe would look very different. Galaxies might never have formed. Stars might never ignite. Chemistry, as we know it, might not even exist. This raises a profound question. Are the laws of physics chosen? Are they accidents, cosmic coincidences that just happen to align? Or are they inevitable, the only way the universe could possibly be? This question isn't just philosophical, it's central to modern theoretical physics. The more we understand about the universe, the more we realize how tightly tuned everything is. Even slight changes in fundamental constants could lead to a lifeless cosmos. The strength of the strong nuclear force, for instance, determines how protons and neutrons bind inside atomic nuclei. If it were just a little stronger or weaker, atoms as we know them wouldn't hold together. The cosmological constant, which governs the expansion rate of the universe, is another striking example. If it were just a tiny bit larger, the universe would have expanded too fast for matter to clump into galaxies. Some physicists argue this is evidence that the laws of nature are selected from a vast landscape of possibilities, an idea we touched on in the previous section with the multiverse. But others ask a different question. What if there isn't a landscape? What if the laws of physics didn't have options to begin with? What if they're the only way anything could be? This brings us to a powerful idea, that the laws of physics are mathematically necessary. In this view, the universe is not just described by mathematics, it is mathematics. Its structure isn't one option among many, but the inevitable outcome of logic and consistency. If you want a universe that works, that holds together, that evolves, that contains stable particles and predictable interactions, then certain rules aren't negotiable. They arise from the requirement that things make sense. Physicist Max Tegmark has been one of the leading voices behind this concept. He suggests that the universe is a mathematical structure, and that all mathematical structures exist in some sense. In his model, the physical world is just one of those structures, the one whose internal logic gives rise to space, time, particles, and forces. Under this framework, there's no need to ask why this universe, because all consistent structures exist. But even without going as far as Tegmark, there's a growing recognition in physics that certain laws might be dictated by deeper principles. For example, the Standard Model of Particle Physics, the theory that describes all known particles and their interactions, isn't a random list of ingredients. It's built from symmetries. Mathematically, it's constructed from group theory, a branch of mathematics that studies how systems remain unchanged under transformations. These symmetries are not aesthetic preferences. They are essential for the theory to be consistent and renormalizable, meaning it doesn't collapse into infinities when used in calculations. Gravity, too, is governed by symmetry. In this case, the symmetry of general covariance in Einstein's equations, which reflects the idea that the laws of physics should look the same regardless of your coordinate system. The geometry of spacetime isn't arbitrary, it follows strict rules, and those rules come from demanding consistency between motion, acceleration, and the behavior of light. This consistency is more than mathematical beauty. It's what allows reality to function. If conservation of energy didn't hold, systems would gain or lose energy for no reason. If quantum probabilities didn't sum to one, then outcomes would be meaningless. Each law of physics is a safeguard against chaos, a constraint that makes the evolution of the universe possible. Some researchers are now exploring whether all physical laws might be derivable from a single principle, a theory of everything. This is the holy grail of physics, one framework, one equation, or one structure from which everything else unfolds. String theory was once a strong candidate, proposing that all particles are different vibrations of tiny one-dimensional strings. More recently, efforts in quantum gravity and emergent spacetime have sought to build space and time from more fundamental ingredients, like information, entropy, or entanglement. If any of these approaches succeed, they may show that the universe isn't built from arbitrary laws, but from the minimum necessary components required to allow something, anything, to exist, evolve, and support complexity. If the laws of physics are not chosen, but necessary, if they are woven into the fabric of logic itself, then the universe is not one possibility among many, but the only possibility that could work. This idea shifts the conversation. It moves us away from asking why things are the way they are, and toward asking why anything can be at all. And the answer, some physicists now believe, may lie not in randomness or design, but in consistency. In physics, consistency is everything. For a theory to be accepted, it must not contradict itself. It must match observations, yes, but even more fundamentally, it must make sense. It must preserve quantities like energy and momentum. It must produce probabilities that add up to one. These are not optional features, they are the rules of the mathematical game. And the deeper we go into the structure of the universe, the more it seems that these rules are not imposed from outside. They are baked into the system itself. Take the example of gauge symmetry, one of the most important concepts in modern physics. It's the foundation of the Standard Model, which describes all the known particles and forces, except gravity. Gauge symmetry is a type of mathematical invariance. It tells us that certain transformations leave the physical situation unchanged. From this requirement alone, that our descriptions of nature should be redundant in specific, consistent ways, we get the electromagnetic force, the weak nuclear force, and the strong nuclear force. The particles that carry these forces, photons, W and Z bosons, gluons, emerge naturally from the math. This is remarkable. It suggests that we didn't invent these forces, we discovered them, hidden inside the logic of symmetry. It also suggests that many features of our universe, the structure of atoms, the stability of matter, even the existence of chemistry, are not accidents. They are consequences of mathematical constraints, and these constraints are tight. If you try to change the values of physical constants, increase the mass of the electron, for instance, or make gravity stronger, you quickly get a universe that doesn't work. Stars don't form, molecules don't bond, time doesn't flow in a stable way. The rules of physics are like a delicate machine, precise, interlocked, and incredibly robust. But here's the twist. That precision may not be the result of tuning. It may be the result of inevitability. If the only stable, consistent, self-contained systems that can exist are those described by certain mathematical structures, then our universe, or something very much like it, was bound to emerge. Not because someone set the dials just right, but because the only dials that stay on the board are the ones that lead to universes like this. This perspective has deep implications. First, it means the universe might not be special in the way we often imagine. It's not just right because it was selected out of a sea of options. It's just the only thing that works. The properties we observe are not arbitrary. They are necessary. There's no other kind of reality that could sustain coherent structure, let alone observers. Second, it reframes our place in the cosmos. In a randomly generated multiverse, we might be a fluke, lucky survivors in a vast statistical ocean. But in a mathematically inevitable universe, our existence isn't luck. It's not even remarkable. It's expected, not because we are central, but because the structure of reality leads naturally to complexity, to stability, and eventually to consciousness. This doesn't mean that humans are destined or that the universe cares about life. It simply means that complexity is allowed, and once allowed, it unfolds. Matter organizes, stars ignite, planets form, information evolves, and somewhere along the way, a being opens its eyes and begins to ask questions. It also opens the door to a strange kind of unification. If reality is math, and if math is universal, then all physical truths are part of a single coherent structure, discoverable, definable, and interwoven. The search for a theory of everything isn't just about compressing physics into one elegant formula. It's about discovering whether reality is the only solution to the deepest mathematical equation that permits experience. We're not there yet. The standard model works, but it doesn't include gravity. Quantum field theory is powerful, but it breaks down at extreme scales. General relativity explains spacetime, but not particles. But the hope is that, behind all of these models, there is one unified principle, one set of rules that had no other choice, not because someone designed them that way, but because they couldn't be otherwise. So in the end, we return to the title of this part, why physics may never have had a choice. It's possible that what we see, the particles, the forces, the unfolding of time, is not a set of decisions made by a creator or a roll of the cosmic dice. It is what reality looks like when it has to be consistent, and that may be the most extraordinary truth of all. Consciousness is the last great mystery. We understand atoms and galaxies better than we understand our own awareness. We can describe how stars form, how black holes bend space, how quantum particles interact, but we still don't fully know how a lump of matter can experience anything at all. And yet, consciousness exists. It's the one thing we are absolutely sure of. You're experiencing it now, the awareness of being, the sensation of thinking, the quiet listener behind the noise. In a video about the origin of everything, consciousness may seem like a strange detour. The universe was around for billions of years before conscious minds emerged. Stars lived and died, galaxies formed, and space expanded, all without a single observer. But in the last century, some discoveries in physics have made that boundary less clear. In certain interpretations of quantum mechanics, the act of observation seems to affect the outcome of physical systems. In a strange and still controversial way, the universe appears to care whether or not it's being looked at. This idea begins with one of the most famous experiments in science, the double-slit experiment. When a single electron is fired toward a barrier with two narrow openings, it behaves not like a particle, but like a wave. It passes through both slits at once, interfering with itself and creating a pattern on the detector behind it. But if we place a detector at the slits to observe which path the electron takes, the interference disappears. The electron chooses a single path. It acts like a particle. The very act of measuring changes the outcome. This doesn't mean that human consciousness causes the change. Most physicists believe it's the interaction with the measuring device that collapses the wave function. But it raises a profound question. What counts as a measurement? What role does information, or the potential for information, play in the behavior of physical systems? Some interpretations, like the Copenhagen interpretation, accept the idea that quantum systems remain in superposition, existing in multiple states until a measurement is made. Others, like the many worlds interpretation, reject collapse entirely, suggesting that all possible outcomes happen just in different branches of the universe. But even in these interpretations, there's no agreement on what exactly constitutes an observer. Is it a conscious mind, a machine, a molecule? Is observation about awareness or interaction? This debate led some thinkers, like physicist John Archibald Wheeler, to propose more radical ideas. Wheeler suggested that observation might be fundamental to reality itself. His participatory universe model imagines a cosmos where observers are not passive inhabitants, but active participants in shaping the structure of reality. His famous phrase, "No phenomenon is a real phenomenon until it is an observed phenomenon," captured this bold view. In Wheeler's later years, he proposed the idea of the delayed choice experiment, in which the decision to observe a quantum particle is made after it has passed through a double-slit barrier. Strangely, the particle seems to retroactively behave differently depending on whether it was observed. The experiment has been performed and its results match quantum predictions. What we choose to measure appears to affect what the system was doing in the past. Again, this doesn't mean consciousness is reaching backward in time, but it forces us to question how information, possibility, and reality interact. None of this proves that consciousness creates reality, but it does challenge the traditional idea of an objective universe that exists completely independently of observation. At the very least, it shows that the act of gaining knowledge about a system changes the system, and consciousness is the only known entity capable of having knowledge. From this strange foundation, some have gone further. The anthropic principle, often used in multiverse discussions, suggests that the universe must have the properties necessary for observers to exist, because otherwise no one would be around to notice. This might seem like circular logic, but in some interpretations, it's not just a tautology. It hints at a deeper connection between mind and cosmos. In a vast sea of possible realities, the one we find ourselves in is not just one that allows for consciousness, but perhaps one that requires it. Of course, there's another perspective, one that treats consciousness not as a cause, but as a consequence. From this view, awareness is an emergent property of complex information processing. It's the result of neurons firing in patterns, of biological systems evolving over time. The universe didn't need consciousness to begin. It just needed the right conditions for life to evolve, and life eventually built brains capable of reflecting on their own existence. In this story, the universe birthed stars, stars birthed elements, elements birthed life, and life, billions of years later, became aware. But even this evolutionary explanation doesn't resolve everything. What is it about matter arranged in certain ways that gives rise to subjective experience? Why should patterns of electrical signals produce thoughts, emotions, a sense of self? This is known as the hard problem of consciousness, and no current theory has solved it. We can map brain activity, simulate intelligence, even replicate aspects of consciousness in artificial systems, but we still don't know why it feels like anything to be you. And that's why consciousness, even if not responsible for the beginning of the universe, might be essential to understanding what the universe is. It's the one part of reality we don't observe from the outside. It's the only thing we know from within. In that way, it may be less a product of the universe and more a mirror held up to it. If consciousness is real, and undeniably it is, then it must be accounted for in any complete theory of the universe. That doesn't mean we need to place it at the center of creation or elevate it to mystical status, but it does mean we can't ignore it as a fringe phenomenon. Consciousness, whatever it is, emerged from the same universe that created quarks and galaxies. It follows the same rules, and yet it also stands apart in one crucial way. It's the only part of the universe that experiences itself. The challenge is that consciousness resists easy categorization. It's not a force. It doesn't carry mass or charge. You can't detect it with a telescope. And yet, without it, none of our science would exist. No theory, no observation, no physics textbook would ever come into being. This leads to a strange symmetry. Just as the universe gave rise to consciousness, consciousness gives rise to our understanding of the universe. Some thinkers believe this feedback loop is more than poetic. They suggest that any universe capable of producing observers must also contain certain informational or computational structures. In this view, consciousness is a byproduct of complexity, and complexity arises naturally from the dynamics of physics. A system that evolves, that stores and processes information, that adapts and reflects, may, under the right conditions, become aware. Not magically, not spiritually, but functionally. This is the view explored in integrated information theory, IIT, one of the leading attempts to quantify consciousness. According to IIT, consciousness arises when information is not just stored, but integrated across a system, when different parts of a network communicate in a unified, irreducible way. In this theory, consciousness is not a switch that flips on or off. It's a spectrum, a measure of how tightly a system's components are linked. A human brain with billions of interconnected neurons ranks high. A thermostat ranks low, but both lie on the same continuum. The idea that quantum states remain in superposition until measured has led some to propose that consciousness itself is a quantum phenomenon. Orchestrated objective reduction, OR, proposed by Roger Penrose and Stuart Hameroff, suggests that consciousness arises from quantum activity inside microtubules, tiny structures within brain cells. This idea remains controversial, and its evidence is unclear, but it reflects a growing desire to find consciousness not in some separate spiritual realm, but deep in the mechanics of nature itself. Still, none of these theories have reached consensus. Consciousness remains a frontier, just like the beginning of the universe, and it's here, at this crossroads, that something interesting happens. Both cosmology and the science of mind seem to circle around the same themes: emergence, information, boundary conditions, and observation. Time, too, plays a central role in both. In the universe, time unfolds space and matter. In consciousness, time unfolds experience and memory. The arrow of time moves in one direction, from low entropy to high, both in physics and in the story of a mind. This convergence has led some to speculate that perhaps consciousness and the cosmos are not separate topics at all, but two aspects of the same story. One theory, still young and speculative, is the idea of panpsychism, the notion that consciousness is not confined to brains, but is a fundamental aspect of the universe. Not that rocks and atoms think, but that all matter has some proto-conscious quality. In this view, complex awareness emerges from simpler forms, just as complex life emerges from simpler organisms. While intriguing, this idea faces challenges. It's difficult to test. It risks diluting the definition of consciousness into meaninglessness, but it reflects a deeper shift in thinking, a willingness to consider that the mind is not an exception to physical law, but part of it. And if so, then the conditions that gave rise to the universe may also be the conditions that made consciousness inevitable. There's also a more pragmatic angle. Whether or not consciousness is fundamental, it is the only lens through which we understand anything. Every theory, every experiment, every equation is filtered through a conscious mind. Even the act of defining objectivity is itself a product of subjective awareness. This doesn't mean reality is a hallucination, but it does mean that the map we build of the universe is inseparable from the minds that build it. And that brings us full circle. We began this series asking, if there was nothing, why did anything begin? We've looked at quantum fluctuations, mathematical necessity, the multiverse, and the idea that perhaps physics had no choice. But now, toward the end, we must admit, everything we've said, everything we've explored, has passed through the filter of a conscious being, not as a flaw, but as a fact. The universe has produced a mind capable of asking where it came from, and perhaps in doing so, the universe is finally becoming aware of itself. That awareness may not change the stars, it may not affect the expansion of space or the dance of galaxies, but it matters, because for the first time, in 13.8 billion years of cosmic history, something within the universe can reflect on what it means to be. And that reflection, whatever else it is real. 13 billion years. That's how long the universe has been expanding, cooling, and evolving, from a dense, hot plasma into stars, galaxies, atoms, planets, and people. We've followed that story as far back as physics allows. We've examined the Big Bang, looked beyond it with bounce models and quantum geometry, and even dared to ask what might lie outside our universe altogether. We've entertained the idea of many universes, and the possibility that the laws of nature had no choice. And through it all, one question keeps returning, like a tide that never recedes. If there was nothing, why did anything begin? Let's start by clarifying what we mean by nothing. In everyday life, nothing is the absence of something. An empty cup, a blank page, a silent room. But in physics, nothing can be surprisingly rich. The vacuum of space isn't truly empty. It seethes with virtual particles, fields, and potential. Even the lowest energy state of the universe, the so-called vacuum state, has structure. It obeys laws, it has dimensionality, it can fluctuate. Some theories, like those involving quantum tunneling from nothing, suggest that the universe could spontaneously emerge from this kind of vacuum, or even from a state with no space-time at all. In this view, the laws of quantum mechanics are always on, and in the presence of those laws, anything not forbidden is allowed, including, perhaps, the birth of a universe. So, if nothing is unstable, and quantum principles are always in effect, then maybe nothing never stood a chance. Maybe the emergence of something, anything, was inevitable. But that raises a deeper question: where did those laws come from? To say that the universe emerged from nothing due to the laws of physics is to assume those laws existed before the universe. That sounds like a paradox. Can laws exist without a universe? Without space, time, or matter? Or are the laws themselves emergent, not eternal truths, but rules that arise once a universe takes form. This is where we must step carefully, because our language, built for apples, trees, and days of the week, starts to falter. We want to ask what came before, but there may be no before. We want to ask what caused the universe, but cause itself may have emerged only after the beginning. We want to imagine nothingness as a thing, a blank canvas, but perhaps nothing is not a place or a state, but the absence of possibility itself. In that sense, the better question might not be, why did anything begin, but why is beginning possible at all? One line of thought suggests that existence doesn't require permission, it just requires consistency. If a universe, or a set of mathematical rules, is logically consistent, then it exists in some form. It doesn't need a spark, it doesn't need a hand to push it into motion, it simply is, because it can be. This view sees reality as the set of all things that do not contradict themselves. But this too is not an answer in the conventional sense. It's not a story with a character and a moment of creation. It's a shift in perspective, from thinking of the universe as something that happened to something that is happening, eternally, across all possible expressions. So why did anything begin? Maybe because nothing else was possible. Maybe because in the space of all mathematical structures, all quantum fields, all conceivable realities, non-being was never truly stable. Maybe nothing was always a temporary pause, a tension waiting to be released, a silence waiting to be broken. Or maybe there was never truly nothing at all. Perhaps what we call the beginning is simply the earliest point we can describe, not the start of existence, but the start of this pattern, this expansion, this unfolding. The Big Bang wasn't the first thing. It was just the first thing we can know about. And beyond it, other patterns, other rules, perhaps even other kinds of something that don't resemble matter or energy at all. There's humility in this view, not defeat. Because if we've learned anything through this journey, it's that the universe does not owe us easy answers. And yet, it gives us something even more powerful, the ability to ask. We are part of this unfolding, stitched into space and time, made from the ashes of stars, tuned by forces that may or may not be universal. We don't watch from the outside, we emerge from within. And the fact that we can wonder, that the question itself can be spoken aloud, may be as close to a miracle as anything else. The universe may not explain why it began, but in its structure, its laws, its patterns and possibilities, it whispers something deeper. That beginning is not the exception. It is the rule. And wherever nothing tried to hold, something found a way in. We saw how quantum mechanics allows something to arise from what looks like emptiness, not as magic, but as a feature of uncertainty itself. We followed cosmologists as they explored the edge of the Big Bang, not as a wall, but as a transformation, a change of state, a shift in structure. We looked into the multiverse and the possibility that our universe is one of many, not because we're special, but because we're possible. We asked whether the laws that govern everything could be the only ones that work, and if so, whether their existence is dictated not by a creator, but by consistency. And finally, we asked what it means that consciousness, the power to reflect, to wonder, to question, emerged from this unfolding. So now, we return to the question that started it all. If there was nothing, why did anything begin? Maybe it's because the very notion of nothing was never truly empty. Maybe the universe didn't begin from nothing, but with nothing as part of its definition. A kind of boundary condition, a placeholder, a state with no shape, no memory, no difference, until difference began, until contrast, tension, possibility emerged, until time could tick forward, until energy could ripple, until being could form. Or maybe the question itself is incomplete. Maybe there was no why, no event, no cause, no agent, no decision. Maybe what we call the beginning is simply the point at which the universe became readable, the point where its behavior could be mapped, measured, and modeled. Before that, not necessarily empty, just inaccessible. And yet, here we are. That's the miracle. That being is even a thing, that existence rose from some state, mathematical, physical, timeless, or otherwise, and unfolded into light, gravity, complexity, and eventually, you, here, now, thinking about it, listening, wondering. The atoms that make up your body were forged in the hearts of stars. The iron in your blood was once part of a supernova. The thoughts in your head, the quiet hum of questions in the dark are electrical patterns echoing across neural networks that were built by evolution, written by chance, tuned by necessity, and carried by generations of living systems in a universe that didn't have to care, and yet somehow made it possible. No one knows if the universe had to begin. No one knows if it can't not begin. But in this moment, on this planet, in this breath, it has. And so, what are we to do with that? Maybe we don't need to answer the question. Maybe we just need to keep asking it. Maybe that's what existence does. It reflects, it loops, it wonders. It builds a brain that looks into the sky and asks what came before the stars. It lies awake at night, not afraid of the dark, but curious about what lies beyond it. Maybe the question, if there was nothing, why did anything begin, is the most human thought that has ever existed. A signal not that we're lost, but that we're alive. And that's how we end, not with a bang, not with an answer, but with a whisper. Something is, and that is enough. Thank you for joining us on this journey through time, space, and thought. If this video helped you rest or helped you wonder, consider subscribing to Night Scientist for more deep, calming explorations of reality's greatest questions. And if you're still awake, let us know in the comments by commenting the word nothing. Now let it go. Close your eyes. The questions will be here tomorrow. For tonight, sleep in the arms of a universe that, for whatever reason, decided to begin.